Alright, so what we're going to do is we're going to talk about inverse functions. This kind of goes along with the whole function notation and functions and everything like that. So this is a decent place to put this. We're going to start with doing it graphically. So this works with, this will help whenever we start doing it algebraically. So the way we get the inverse graphically is we're going to kind of do this with geometry to start with. You guys kind of remember reflections? What we're going to do is we're going to do reflection across the y equals x line. So this is the line y equals x. Now, in geometry, the rule for doing a reflection over y equals x is that we go straight across that line. Let me take this point and we'll do the rule with this point and then we'll make it easier. When we did reflections, this distance, we go straight across so it makes a right angle. And we do the same distance on the other side. Now, my line is a little off, so I'm going to make this work, but this distance and this distance has to be equal. So my point would be right there. Again, mine is definitely off. But it'd be at 0, 2. So if I did that with this point here, it would go to 0, negative 2. This point, wherever it goes across, it would go to negative 4, 0. So this gets switched so that it looks like this. My drawing is really, really terrible. What I wanted you to notice was this point here, I'm going to make this point really, really big so it does what I want it to. Notice points on the line stay on the line, so they don't move. Which makes sense because what I'm doing here is ordered pairs swap places, right? 2, 0 becomes 0, 2. And that's how the rule for this reflection worked. That's the rule for that reflection. My drawing is really, really terrible. This point would go over here to 5, 3. This point stays where it is on the line, and again, I'm going to make a big, huge dot to make it work. This point goes all the way across to over here, which would be 5, negative 3. So that's how inverses work graphically. If I had taken a little bit more time with my picture, it would have looked better and prettier and not a mess. But this is the idea I wanted you to get from this, is that we're doing a reflection. When we do a reflection with this graphically, our order pairs switch places. Now, while we're working on this graphically, I want to do one more thing with this. Let me draw a smaller version of this. That's not a mess. There is my original function, right? And this is my inverse. Which I can't spell. Okay. Now notice with the original, the original is a function, right? How can I tell that the original is a function? Yeah, it passes the vertical line test. My inverse, however, is not a function, right? Okay, now, I want to get 2 points out of this. First, it would be wonderful if I could tell that the inverse would not be a function without having to graph it. Because sometimes we want to know whether the inverse is a function or not from the original graph. Okay, so notice whenever I do this vertical line here to test this, what does that vertical line translate to in the original? So if I would go backwards, this is tilted like this. If I go backwards, what is that vertical line in the original? A horizontal line. So in the original, that same line would be a horizontal line. So I can tell that the inverse is not a function with the original graph by using a horizontal line test. Mm-hmm. So, on the original function, if I use a horizontal line test, the horizontal line would translate into a vertical line on the inverse. So using a horizontal line on the original is doing the same as using a vertical line test on the inverse. So by using a horizontal line on the original, that's telling me whether or not the inverse is a function or not. So I want to come back to this, but let me do a couple examples of that. So I'll bring that page back. Give me a second. So, is the inverse of that a function? Yes. Because if I take a horizontal line anywhere on that, it only crosses it at one point. So that means that the inverse is a function. Or your horizontal line test, because the inverse would actually look like this. This is what the inverse would look like. The inverse would look something like this. That is a function, correct? But again, we want to know that without having to worry about getting this. So the horizontal line test tells us this function, because every single one of these horizontal lines translates into a vertical line on this picture. Okay, that's not a function, right? But is the inverse a function? Yes. The inverse is a function because any place I put a horizontal line, I only cross one point. So a function, or the original doesn't have to be a function in order for the inverse to be a function. And if the original is a function, does not mean that the inverse will be a function. Okay, is the inverse of that one a function? No. Because with this one, right there, it failed. Okay, so does that part make sense? So we have vertical line test to test a function to see whether it is a function. Horizontal line test tests whether its inverse will be a function. So that we don't have to find the graph of its inverse. I mean, if we have the graph of its inverse, then we just do the vertical line test on that graph. But we don't have to go finding, all our different graphs. So we can just take one graph and know whether the inverse is a function or not. You guys are being too quiet. I'm scared. Okay, so let's go back to this. I want to talk about this. You're not going to be asked to do this. But this is a parabola, right? It's quadratic function. Okay, what is the inverse of a quadratic function? A square root. Well, we just said that a quadratic function does not have an inverse that is a function, right? Is a square root a function? Yes. So you just contradicted yourself. What's wrong with all that? Because you just told me that okay, this doesn't have negative values. It doesn't go over here. But square root is a function. But this is the inverse of this. Oh my God, we just broke math. Okay, what we do is we restrict it to make it a function. Because a lot of times in math doesn't work unless something is a function. So what we do is we take things where their inverses are not functions and we force them to be functions. So notice that whenever you take a square and you square root things, you have to do the plus or minus, right? So what we do is we cheat. We say, I don't want to do that. I'm just going to do this. Because this is not a function. This is a function. No, you can't. But the world does. Okay, whenever we introduce a square root into a problem, in order to get all the answers, we have to put a plus or minus. But whenever we're doing things with graphs and stuff, in order to create a function, what we do is we do this, because the graph of this is this. Whereas the graph of this one is this. So we restrict the range of it so that it becomes a function. Again, that's not something that we're going to worry about. It's not something I'm going to ask you to do right now. It's something I want you to realize that is happening. It's food for thought. It's just pre-calc. I want you guys to realize that there's more going on in the background than sometimes you think about. So I just want you to realize that, because right here I just told you that this is the inverse of an x squared. Yet here in a little bit we're going to talk about how the inverse of a square is a square root. So that's actually a contradiction. But at the same time it's not a contradiction. Okay. So there's everything graphically. So let's move past graphically. The other thing is I want you to see this definition, and this is kind of graphically also. We'll start it off graphically, and then I'll give you kind of a word definition of it. And then I promise we'll move past graphs. Okay, one-to-one functions are very special functions. They're special functions because both the original and the inverse are both functions. An example graphically of a one-to-one function would be that. What happens with these is every x value only has one y value, but also every y value only has one x value. So that's kind of your definition of a one-to-one function. So that's what you have to have in order to be a function, right? So in order to be a one-to-one function, you just have to have it both ways. So those are special functions. We're not going to deal with them a whole lot in here, if really at all. It's just something that, it helps you in further classes if you've been exposed to things like that. Okay, so now the actual work. Because, we've had all this, but you guys really haven't done any work. Okay, so before we do anything, you need to know what the function notation of this looks like. So, if this is the original function, the way we denote the inverse is like this. So, this means inverse. So you're going to have two main types of problems. You're going to have a type of problem where you're going to have to find the inverse, and you're going to have a type of problem where you have to check to see if two things are an inverse. So let's start out with the type that we have to check. So what they're going to do with these is they're going to give you two functions. So they'll give you two functions like that and ask you whether these functions are inverses or not. And you have to double check and see if they are. So here's the rule for checking. If functions are inverses, then this is what happens. If I take a function and I compose it with its inverse, I get x as an answer. I should probably write that out the other way also. Now, the rule actually says that you have to check both directions. I just wrote it down both different notations. That's the only reason there's two different things there. Okay. There is a reason for checking both directions. I'm going to tell you right now, for everything that we're doing, if you just check in one direction, you're fine. There's no reason to check in both. Wherever you get up into super high mathematics, there is a reason, but we're nowhere close to that. So at this point, you can check in one direction and you're fine. I'm not going to make you do all the extra work of checking both. So what we have to do to check these is just do a composition. It doesn't matter which direction you do the composition. So I'm just going to do this. F composed with G of X. If I get X for an answer, then they're inverses. If I don't, then they're not. It's just that simple. If I get X for an answer. So this is what I'm looking for. I need X for an answer. So according to this is the way it needs to look. And again, this is the way I set it up. I could do it the other way if I wanted to. So I got X. Huh? On this, that's the only answer I could get. If they're not inverses, then you'll get something else. I can do another example where they're not inverses. Yeah, if we did it the other way, you would get the same thing. No, you don't have to check it both ways. So if you did it the other way, you'd still get X.
So where do you use those checking things? The formulas for checking, what do you use those?
Where would you use this, like real life?
Not in like
In the homework, they're going to specifically say, here are two functions, are they inverses? And this is what you do.
Do you use the formulas up there?
Yeah, I mean, one or the other. I just wrote it out two different. This means the exact same thing. All you have to do is compose them and see if you get X or not. So here, I can do another one where you don't get X. So if I try doing those two, I would have that. Whenever I square it, the square root would cancel out. But then I get x plus 4, so that means that these are not inverses. So anytime you would compose them and get anything besides x, they're not inverses. Okay, finding inverses, what we're doing is we're using the idea that we had from graphing. When we had graphing, whenever we reflected it, what did we do with each of the ordered pairs? You switched them. So that's what we're doing with this. So graphically, we did this with each of our ordered pairs, right? So that's what we're doing here. We're going to do that with our equations. So what I'm going to do is, first of all, I don't want to mess with writing f of x all the time. So I'm going to switch this to y. Yeah. Okay, now, to get my inverse, all I need to do is switch my x and my y. You now have your inverse. That step there, that created your inverse. You're not done, but that is all that it takes to create an inverse. That is it. That is how easy it is.
Some of our homework problems involve us putting it in point slope order.
No. You're going to be given a function like this. You're going to be asked to find the inverse. So your first step is get rid of this and then just switch the x and the y. That has literally created the inverse. Now, what you need to do in order to finish this is you need to get it back into function notation. In order to get it back into function notation, you need to solve for y again. So the first step, creating the inverse, is easy. The work comes in getting the y back by itself. Now, on this one's easy. All right, I subtract the 5, divide by 7. If you wanted to leave it as x minus 5, all divided by 7, I don't care. So you could also have it looking like this. Okay, now I start off in function notation. I want you ending in function notation because I want you to get used to using the f inverse notation. So this is what I want to see for an answer. So I want to see the function notation. Okay, but those kind of problems, all they're going to do, they're just there to test you really with your algebra skills for solving for y. Creating the inverse is easy. You just have to switch your x and your y. The rest of it is again, just testing your algebra skills. Yep, that's your answer. Okay, this may take a little bit of explanation. Let me get it written down and then I'll explain it. Okay, pretty much throughout this, they're going to ask you to do it algebraically and graphically. I'm not asking you to graph anything. So 13 through 23 has a part A and a part B. Part A asks you to do it algebraically, part B asks you to do it graphically. So on 13 through 23, you only have to do part A. Number 31 I think is fine. Yeah, number 31 is fine. 39 through 63, again, anything that they ask you to do graphically, don't do. Just find the inverse algebraically.